The talk today is our recent research results showing that there's a new large radical source of chlorine atoms over the North Atlantic. And this is the ISOMO project, which is funded by Spark Climate Solutions. We had a kickoff meeting in June of 2022 up in Helsingør. And then this project, I'm the PI, and we have partners in Utrecht, Oceans X in the Netherlands, Maersk, Acacia Impact Innovation, the Spanish Research Council, Cornell, and Stony Brook University. So kind of a new project, but we are mentioned now in the recent Maersk sustainability report. They say, supporting ocean and climate science, Maersk continues to leverage our vessels and ocean networks in support of ocean and climate science through long-standing partnerships and research organizations. They supported the Oceans X Exploration ISOMO project, exploring solutions that could one day recreate the natural process of methane oxidation. That's what I'll tell you about today, which removes methane, a greenhouse gas, from the atmosphere. In 2023, a crew on Maersk vessels crossing the Atlantic collected 280 samples for analysis. This makes us the largest atmospheric sampling network in the world, next to NOAA in the United States. So we have a very large network, thanks to Maersk, helping scientists understand why methane oxidation occurs at an increased rate over the sea and in areas with high iron content, as well as the impact of dust from the Sahara Desert over the Atlantic Ocean. So that's the mechanism I'll tell you about here. So we have something to do with iron and Sahara Desert dust and the marine environment, and this is having an impact on methane. So if we think about methane, usually carbon dioxide gets all of the attention as far as being a greenhouse gas, but methane is also very large. It has about 3/5 of the global warming impact that carbon dioxide has. And it does that at much lower concentration. And so it has a instantaneous warming 120 times that of carbon dioxide, or a global warming potential of 84 on a 20-year timescale. So that's on a mass per mass basis. The atmospheric concentration is increasing. You can look at the pre-industrial concentrations, maybe around 600, 700 parts per million. We're now around 1,900 parts per billion, over 1,900 parts per billion. And so this has been going up, mainly due to agriculture. And, you know, if you contrast this with carbon dioxide can be separated from an airstream as part of carbon capture. But chemically, that's much more difficult when you're dealing with methane. And really, there is no good way to separate methane from air if the concentration is below the combustion limit. If it's above the combustion limit, of course, you could burn it as fuel, and it's valuable for that reason. But there's not a lot of good things to do with low concentration methane. And this is just to give you a picture of what's been happening with methane in the recent past. And so there was a lot of discussion about this in the early part of the century because methane in the atmosphere stopped increasing. And as the second most important greenhouse gas, if you would like to do a forecast of climate in 50 years or 100 years, would you extrapolate from that plateau, and just go flat going forward? Or the recent past has shown that the increase has come back, and actually that the rate of increase is increasing. So there's a lot of debate about the sources of methane and the reason for this increase in the literature, and if it might be some kind of a feedback between changes in the hydrological cycle and changes in temperature on the natural sources of methane to the atmosphere. This is an overview of the methane budget. So you can see that the anthropogenic sources are in orange. Some methane is coming from fossil fuel production and use, and also some from agriculture and waste. And then the natural fluxes are in green. And in each case, there's two numbers that are estimated. One is the bottom-up estimate, and then we have the top-down estimate. And you see there's some uncertainty between the top-down and the bottom-up. To get the top-down view, you could take a sample of atmospheric air. You would look at the abundance of 13 carbon in the methane and perhaps also deuterium in the methane. Then you have a certain isotopic enrichment in the sources of methane. And so you could back calculate where the methane must have come from in order to give you the atmospheric composition. So that's the top-down method. The bottom-up method is just to count the number of cows, count the number of garbage dumps, and then add up all of these things in a big budget. And hopefully they would agree, but they don't quite agree. Now, one of the things with methane is that, some of the sources are pure methane. This could be a natural gas pipeline. And these high concentration sources starting at 1,000,000 parts per million. Some is coal ventilation air. You have abandoned coal mines. A lot of methane is coming out. So these high concentration sources are about 1/4 of all of the emission sources. Now, the combustion limit is at 4%. And that means that if you wanted to do something for climate, you would have to destroy the methane below the combustion limit, 44,000 parts per million. And you can do that using a combustion bed, a high temperature catalyst. Those would probably get you to a few thousand parts per million. But there's still a very large number of sources, about 3/4 of all of the methane sources, that occur at concentrations below 1,000 parts per million. And so there we would like to have a new technology. I can tell you all about it on another occasion that would be able to destroy this low concentration methane, especially from the agricultural sector. Now, this story begins with some people who were on Barbados sampling atmospheric air and analyzing the carbon monoxide in the atmospheric air. They were doing this in the late 1990s, and they determined the amount. Somebody has their microphone on. They determined the amount of 13 carbon in that carbon monoxide. And when they did that, they found actually extremely low abundances of 13 carbon in the carbon monoxide, less than 34 per mil depletions. And this was the most 13 carbon depleted carbon monoxide that had ever been found in the world. And of course, they analyzed the data, tried to figure out what was causing this. And they concluded that this was evidence of some kind of a source of that carbon monoxide, such as chlorine catalyzed destruction of methane. Now, usually atmospheric methane would be reacting with the hydroxyl radical, and there's a very small kinetic isotope effect when methane reacts with hydroxyl radical, 3.9 per mil at room temperature. If the methane reacts with a chlorine atom, there's a kinetic isotope effect of 6.6%, so a very large KIE. The products go through, some short-lived radicals, and formaldehyde also has a short life, and it shows up as carbon monoxide. And so these depletions, they're saying, is evidence of chlorine reacting with methane. And then you see that there's extreme depletions, but only at a certain time of year. And they saw this on Barbados, but they did not see it on the Canary Islands at Tenerife. So it seems to be local and seasonal and episodic. And those are the things that we're going to try to explain. Why is this 13 carbon signature local, episodic, and seasonal? All right, we have a mechanism, and this is the iron salt aerosol mechanism as part of ISOMO. The overall idea is that mineral dust combined with sunlight and sea spray aerosol is going to generate oxidized chlorine in the atmosphere. And that happens in the way that iron will be released from the minerals. We have sea spray that has a lot of sodium chloride, and under acidic and oxidizing conditions that you would have in a small water droplet in the marine boundary layer, iron will be in the form of iron 3. So iron 3 in a chloride-rich environment is going to form a series of iron chlorides, and these absorb visible light and UV light. And when they do that, there's a ligand to metal charge transfer absorption, right? So the electron is actually going from chloride onto iron. So chloride becomes chlorine, a chlorine atom. The iron 3 becomes iron 2. Very interesting. So the chlorine atom, eventually these build up and they escape as molecular chlorine into the gas phase that can be photolyzed by sunlight, making chlorine atoms that would react with methane. That's one part of it. The iron 3, there's normally a process called the Fenton process that consumes hydrogen peroxide and interconverts iron 2 and iron 3. And that means that the iron 2 product will reform iron 3, making the process catalytic in iron. Now, when a chlorine atom reacts with methane, it makes hydrogen chloride as the product. That's also taken back up into the particle, meaning that this process is also catalytic in chlorine. And so under the right conditions, you could have a very efficient process for converting chlorine that originally would be from sodium chloride from sea spray into chlorine atoms and deplete a lot of methane in the atmosphere. So we've done some work in order to characterize this mechanism. We have these individual equilibria. So you could have iron 3, monochloride, dichloride, up to hexachloride are described in the literature. We did some modeling of the aqueous phase equilibria. We find that the iron dichloride, iron 3 dichloride is the main species at these acidic pHs. These absorb sunlight. We calculated the absorption spectra using ab initio methods and the thresholds for dissociating that. We also just took iron chloride samples into the laboratory and used bandpass filters to photolyze them at specific wavelengths. And then we could look at the chlorine generation or the methane removal as a function of the wavelength of those filters. So we see a maximum, could be around 440 nanometers, something like that. These are the Fenton reactions. You see that by oxidizing or reducing the iron chloride, we're bypassing 1/2 of the Fenton catalytic mechanism. And this happens to be the half that's producing acidity. So normally the Fenton mechanism would be pH balanced. But if we do this photoreaction, we would now be producing base, and that could take the aerosol out of the favorable acidic region and move us over into the region where iron oxide and hydroxide would be more stable. So the process might be acid limited, but there are a lot of sources of acidity in the atmosphere. This could be hydrogen chloride that would be taken up back into the droplets, or nitric acid or sulfuric acid. There's an escape mechanism here. And then again, we're activating that chlorine using sunlight. All right, some fun chemistry. And then we go into the atmospheric chemistry. And the idea here is that there's a lot of dust being formed over the Sahara. This is lofted high into the atmosphere, into the upper troposphere. It is going towards the new world from the old world, and then it subsides in the Caribbean. And that means that this mineral dust is now mixing with the marine boundary layer and with sea spray aerosol in the marine boundary layer. This circulation changes depending on what time of year it is, what season it is. And there's one pattern that we see in June, July, August. There's another pattern in the late summer in September, October, November, where we have much better penetration and a longer path through the marine boundary layer before we get to Barbados. Right, so the idea is we're lofting the dust, it descends, it mixes with the salt, then we get this photoreduction process going on. we're making the HCl and we're oxidizing methane. We remove some ozone at the same time, and we're losing this to deposition. And overall, we're making this 13 carbon depleted carbon monoxide. All right, here is the flask samples that they obtained on Barbados in 96, 97, and 98. They published that in 2003, so just over 20 years ago. And so there was a mystery for 20 years where that chlorine could be coming from. If you use the standard chemistry, what is known about the atmosphere, you have seasonal cycle in the sources of carbon monoxide and a cycle in hydroxyl radicals in the atmosphere. That has a kinetic isotope effect. Biomass burning gives a certain 13 carbon signature in the carbon monoxide. All of these things give you the blue line. So the blue line is the standard chemistry. Now, the observations are these squares. And so you see that sometimes there are excursions. And then we did a model of this mineral dust mechanism making chlorine atoms through the sea spray aerosols, and that is the gray line. So the gray line is predicting these seasonal and local excursions. And you can see that the observations did not see those highly negative values in 13 carbon on Tenerife, but we're predicting that some of these could occur. And the difference there depends on the altitude at which you sample the air. And you're in a different part of the airstream if you're, at the top of the mountain or at sea level. And so now we're going back. There's a very nice monitoring station on Tenerife run by our friends at York in the UK. And so we're going to be getting some filter samples and some flask samples and analyzing the air there and figure out if it really is this altitude dependence. Now, we ran a global model in order to figure out what was going on. And this model had dust. It has the meteorological data from these years that were involved. And we were able to simulate this mechanism and predict the formation of chlorine atoms. And, this is in units of 10 to the 4 atoms per cubic centimeter. Some of that chlorine reacts with atmospheric ozone. And so ozone is a precursor for the formation of hydroxyl radicals in the atmosphere. So we're predicting ozone depletion due to the MDSA mechanism in this region, but also depletion in the concentration of hydroxyl radicals. And this means actually that you could end up with more methane, since usually methane is reacting with the hydroxyl radicals. Overall, we would have methane loss, and especially strong loss, over the coast of Africa. And then by the time we get over to Barbados, this air has been processed, and we're able to predict what the outcome is. So if we bring all this together, this mechanism is able to explain some observations that couldn't be explained before. One of them is that there's very large differences in estimates of how much methane is removed by chlorine. Some of these are top down, some of them are bottom up, but basically there's about a factor of 4 difference in the amount of chlorine in the atmosphere, depending on which method you use. So there's definitely room among current understanding for a new chlorine atom source. We discussed this, the episodic, seasonal, and location-dependent 13 depletion in carbon monoxide. There's an anomaly in the carbon monoxide to ethane ratio measured at Cape Verde. And the strange thing is that carbon monoxide does not react with chlorine atoms, whereas ethane does react with chlorine atoms. Well, both of them react with a hydroxyl radical. So if we have a perturbation, if there's additional chlorine, it's really going to skew that ratio. And in this paper, they said there's some unknown source of chlorine, and our model seems to resolve that. In addition, one of the products of this would be HOCl. We're able to explain that using our model. And there have been observations of ozone depletions in association with dust storms. And this, again, could be due to this additional chlorine produced by the MDSA mechanism. Overall, we find that 3.8 teragrams of chlorine are being produced over the North Atlantic, making it the single largest source of chlorine in the region. And if we apply that globally, it increases chlorine production by roughly 41%. So very large impact. Since only a few percent of methane are reacting with chlorine atoms, you could say, so what? We have a slightly larger loss of methane. That's great. That's true to a certain extent. The larger impact of this is because a lot of these budget estimates to find out where methane comes from are relying on the isotopes. And the idea here is that you can get atmospheric air, you can measure the abundance of 13 carbon in that air, and you might expect that that would be due to the sources of methane in the air. And you could even correct that for the kinetic isotope effect of the loss processes of methane. And then that corrected composition should reflect the contributions from the different sources. And a lot of these sources are very depleted in 13 carbon, especially the biological sources. And this includes wetlands and it includes cows, right? And one of these is boreal forests, so the northern forests, and it's tropical wetlands. And we have cows and we have rice paddies. So those are the main things. The fossil fuel sources are not as depleted in 13 carbon and actually above the atmospheric abundance of 13 carbon. So basically, a 1% increase in methane loss by chlorine would shift this abundance in the sources of methane globally by 0.5 per mil. So that's the true implication of this. And what it means is that the top-down models have misallocated or failed to allocate something like 12 teragrams per year of methane to 13 carbon depleted to the very carbon depleted biological sources of methane, such as agriculture and wetlands. And you can see here that that would be a 10% addition to a source like this. Or if we have wetlands here coming in at about 150, 180 teragrams per year. So it's a significant shift. Now, there's a lot of debate about why methane is going up. And some people are saying that a lot of methane is being made by tropical wetlands, by wetlands in Africa, and by the Amazon rainforest. And there's actually an increase in rain because of climate change and intensification of monsoon rains, for example, in that region, in addition to increased temperature. And so they say that this could be a sign of a feedback producing more methane, a positive feedback in the climate system. Now, at the same time, some of that has been masked by this chlorine atom effect. And not only that, but actually the amount of dust, the dust loading in the atmosphere has been increasing in time due to the growth in deserts and due to increase in wind speed. And so what we're saying is in agreement with other people like Ewan Nesbitt at the University of Cambridge, who has been doing measurements of the wetlands, of the tropical wetlands, and saying that that is the driving factor behind it. All right, that's the finishing of that. Another thing is to think forward a little bit. And here we've done a bit of science fiction or, chemistry fiction. And we're saying, how much additional chlorine would you have to add to the atmosphere in order to really have an effect on the amount of methane? And some people have proposed adding chlorine to the atmosphere as a kind of geoengineering. And I'm not suggesting that we do that, absolutely not. I'm saying that we should understand the technical details of it and perhaps some of the hazards of it in order to evaluate whether that would be a desirable option or a undesirable option. So we did some modeling. We published this in Nature Communications last summer. We found you'd need a lot of chlorine in order to do that, but there would be an added benefit because you would remove ozone at the same time as you're removing methane. And ozone is tropospheric air pollution. So we would have better air quality in the troposphere. Ozone is also a powerful greenhouse gas. And so the cooling from the decrease in methane would be equal to the cooling from the decrease in ozone. So we get like a 2-for-1 out of that. And we use some of the same scenarios as the IPCC uses in order to do these calculations. So we're doing global modeling and predicting the future composition of the atmosphere. All right. That study said that the chlorine would be released as a uniform flux from the surface. But some of the methods that are being proposed would not be a uniform flux. They would be a plume. And one example is that the fuel that's used by container ships, the bunker fuel or heavy marine diesel oil, naturally contains some iron as an impurity. Or some people have proposed that you could increase the amount of iron. For example, ferrocene is used as a fuel additive. And if you added some ferrocene, you could increase the iron content in the exhaust from the ship. So we did modeling in order to understand how atmospheric chemistry would behave under high chlorine conditions. And if you take our course in atmospheric chemistry, you'll learn about how methane is being oxidized by the help of nitrogen oxides and HOCl radicals. So we have HOCl radicals and NOx radicals, but here we're introducing new radicals, the CHLOX radicals. So that could be chlorine atoms, it could be chlorine monoxide, chlorine dioxide makes an appearance. And then this chlorine monoxide can take over the role that nitric oxide is usually playing in the atmosphere in converting the methyl peroxyl radical into methoxy. That's one thing that can happen. We did this modeling. We wanted to find out the chemistry that's occurring in the plumes. It turns out that that chemistry is dependent on the level of NOx in the atmosphere. And sometimes adding additional chlorine makes the atmospheric reactivity decrease. And that's because of the suppression of the hydroxyl radicals. And this means that we would be removing negative, 0.3 methane molecules per chlorine atom added if we're in this region. But if we're at very high NOx levels or very low NOx levels or very high chlorine additions, then we're able to remove additional methane per chlorine atom that's added. That's important because it would matter where your ship is. So this leads to the conclusion that less iron in shipping routes would mean increased methane concentrations. Would mean increased methane removal. And so, along the main shipping routes that we have in the world today, if we were to decrease the iron impurity in the fuel, that would have a positive impact on climate. But conversely, if you're in this green region, more iron would actually increase the methane removal. Ozone levels are lower, and so adding the chlorine will have a direct impact on methane. So you could go in both directions with this. And I think it was just lucky that this Sahara dust was reacting over the green region in the North Atlantic in order to produce these samples that we were seeing at Barbados and able to explain that. We're also predicting that there's going to be a larger effect farther south. And there's actually a very large atmospheric observatory. There's a tower, the Atto Tower, above the Amazon rainforest. And I forget the exact height of this tower, but we've now started taking air samples from the Atto Tower. and then we're analyzing the 13 carbon abundance. And so the question is, could we confirm this mechanism in the atmosphere today by doing a field study? And so we're doing that study. We've recruited a lot of seafarers who are aboard ships, and these could be Maersk ships. We're also working together with Stolt, and we send them a flight case that has an air pump and some sampling flasks. They take samples of the air, and then these are sent to the mass spectrometer in Utrecht, and they analyze the 13 carbon abundance. And what we see is that this chemistry is definitely occurring today. Here we have a satellite map of the amount of mineral dust in the atmosphere. And then this transect going over to South Africa is again showing these very large 13 carbon depletions in carbon monoxide. All right, I'm nearing completion of this talk. We're also looking at 18 oxygen. That helps you to know how much of the carbon monoxide is from biomass burning. We are seeing different patterns depending on where the air is coming from. We're preparing this for publication right now. We were so lucky that we have a colleague, Thijs Seuling, who's in the middle of a desert, and he's able to obtain dust samples from the Arabian desert. And you see, we did this calculation where we found that 1 kilogram of photoactive iron released from the Sahara dust over the North Atlantic, that would remove about 40 kilograms of methane during the time that it's in the marine boundary layer. And that has an impact of 1 ton of carbon dioxide equivalent. If you assume that all mineral dust in the world reacts in the same way as the Sahara dust, you get our finding of a 41% increase in chlorine over the ocean globally. But that probably is not true, because Arabian dust is going to be different from Sahara dust, or the Gobi Desert dust is going to be different. So what Thijs has done is to do an elemental analysis. We can determine the iron content of that. And then we have a student, Natasha Pedersen, and she's going to look at the photoactivity of the iron coming from this dust as part of her bachelor project. So we're looking forward to those results. And then I think there's some important interactions of this mechanism with climate change. One of them is, as I mentioned, these changes in dust loading in the atmosphere due to growth of deserts, changes in wind speed and circulation, changes in rainfall. There's also an important interaction with anthropogenic air pollution. And if you think of the Gobi Desert, and the dust there is mixed with a lot of air pollution, that would include a lot of acids, could be nitric acid, could be sulfuric acid, that could accelerate the process. And it's also going to be a lot of NOx under those conditions, in addition to organic acids. So we're going to use the European photoreactor in Valencia, Spain, and study some of these interactions. Our PhD students, Louisa and Marie, were there about a month ago, suspending Gobi Desert dust into the photoreactor and looking at the reactivity. We would like to do further studies to characterize these changes in the impact from anthropogenic iron from industry and shipping due to interactions with the local environment. And there's also changes in wind speed will change the sea spray aerosol. There's a lot of people who have been involved in all of this research, and definitely a huge thank you to all of them. And thanks also to all of you for listening to my talk.